what I want to do now is to go over a number of different natural convection configurations. Each of these configurations has a different formula. So in your formula sheet, you're going to see lots of things. Vertical plate, horizontal plate, inclined plate, enclosure, all those type of things. So you look at the problem. What is this? What type of problem do I have? It's a vertical plate, it's an enclosure, whatever it is. And then you do the plug and chug. Here we have configurations other than the vertical plate. So how about an inclined plate, right? And the inclined plate is interesting because now you have an up and a down, right? So it depends on whether the plate is cold or the plate is hot. You're going to have some part of the fluid that is, I don't know what the best term to use is, so I call it kind of compressed, right? So here, as the air gets cold or the fluid gets cold, it gets compressed. Here it gets compressed. But the other one is free, right, and wants to expand, right? In this case, the cold fluid would be falling down and there is turbulence. These two sides behave very differently. The side that is compressed, right, behaves like a normal vertical plate. Nothing to write home about other than because it is inclined, the effect of gravity is reduced, right? So you do the exact same formula, but you replace gravity by the projection of gravity on this axis, right? So if it is 45 degrees, is gravity times square root of 2 over 2, right? It's going to be slightly less intense convection. The other part in which we have turbulence, there is no universal correlations for that. At least that's what the book says, right? But if you were to have, say in the exam or in life, an inclined plate, this part in which the flow is compressed, you know how to do it because it's exactly all we have been doing so far. Just change the value of gravity, right? And the other part you say, I don't know, and you don't know. So we're even. All right? You see it? So look at this. We've been talking about the theory of a vertical plate. And then we did a cylinder using that. It's very powerful. And now I say, okay, it's not vertical anymore, it's inclined. And for half of that, everything is the same as before. Very powerful concepts. Now, let's say that the plate is not inclined, but it's flat. Right? For example, in my life doing welding, you typically weld in the flat position, and the plate gets hot, and it loses heat from the top and heat from the bottom. Right? How would you calculate this heat exchange? Here you go. We got it. Right? This horizontal plate. And guess what? You have, if Rayleigh is relatively small, you have a correlation that says Rayleigh to the 1/4. If the Rayleigh is a little bit bigger, now you have a correlation of Rayleigh to the 1/3. You can plug and chug, but you know what that means, right? If it doesn't speak to you, because it should. Look, this 1/4 is the 1/4 of laminar that we've been seeing all along, right? This 1/3 is the 1/3 of turbulent that we have been seeing all along, right? I think that's where the interesting thing is. The book is not telling you what is laminar and what's turbulent. But looking at this, you know, these correlations are the same ones we've been very familiar with. Now, for the lower, you have the same thing, right? But you have this correlation to the 1/5, right? Now it's a different thing. These correlations have something especially interesting, that people did experiments and they saw that when you do this Rayleigh number based on some characteristic length, depending on how you choose the length, you can do many different plates, whether it's a circle or a square or an ellipse or something like that. Crazy shapes, I'm not too sure, but shapes that have relatively small curvature in the edges, yes. So you would calculate the characteristic length for your Rayleigh, right? Here's Rayleigh, that you need an L, as area over perimeter. And if you do that, area over perimeter, right? That gives you a length. You put that in there, and you can calculate convection on the top or in the bottom of a circular plate, square plate, rectangular plate, elliptical plate. Very, very, very powerful. And what you get to see also is if you were to have a hot plate, right? The upper side, right? It has a quite significant, quite a lot more convection than the bottom. And the reason is you have all these recirculating flows as they go up, but in the bottom, you don't have as much of an intense advective flow, right? And as you see here, if this is hot, right, and you have all these flows going in, they enhance convection. We're going to see when we talk about phase change that this is a mechanism that happens in boiling too. As you make a bubble and the bubble flows, it floats, it creates a recirculating flow that enhances convection. That is the highest amount of convection you can have when you're at the right point of boiling. So this is not boiling, right? But you have, because of these turbulent flows, this recirculation that enhances. But the plug and chug is trivial. Look, a constant times Rayleigh to some exponent. You calculate Rayleigh, done. Very powerful, so easy, right? Look at this. Now, horizontal cylinders, right? In an horizontal cylinder, you're going to have a formula too, right? To calculate Nusselt, and you know the methodology, right? The whole point is you get your configuration, you get your parameters, you calculate Nusselt, and then you unpack it into an H. And then once you have H, you can calculate the total heat transfer, whatever system. And I mean, this is super dry. Look, it's just a catalog of formulas here. But what do you get to see here, right? Look, Rayleigh to the 1/6, and then it's squared. What is that? Rayleigh to the 1/3. Again and again and again, right? Many people just see like random numbers there, but they are not random numbers. Are always the same numbers, right? And in this case, Prandtl number appears. So air is 0.7, water is about 7 in Prandtl. So this order of magnitude indifference, these type of formulas capture it for both air and water. You have that the bigger Rayleigh number, the bigger the Nusselt. All these things are familiar. There's one interesting thing here. So if you say Rayleigh is 0, for example, in these formulas, if Rayleigh is 0, you would say Nusselt is 0. But we know it's not true because we would have convection. In this case, they just say, hey, don't go below 10 to the 4 in Rayleigh. So below 10 to the 4, they say, I'm not talking. These other guys say, you want Rayleigh of 0? Sure. And that's why they have this 0.6 here, right? So when Rayleigh is 0, you still have some amount of convection in this formula, right? That is an interesting thing. And you can have also some other formulas that are tabulated, right? Again, C, a constant times Rayleigh to the n, as usual. And guess what? And the book doesn't tell you this, but isn't this obvious? Look at this. When Rayleigh is very big, is when you have an intense flow. Is when it's turbulent, right? What is the exponent? 0.33. This is awesome because next time, if you have no idea what to do and nobody gave you a correlation, I'll take a stab at these type of things. Look, if the Rayleigh number is intermediate, right? What do we have? Laminar, 1/4. Those are not random numbers. Now, these random looking numbers, let me tell you what's going on. And this is one of the problems that Ying has, actually. When you go for very small Rayleigh numbers, and in her case is something else, right? The problem turns into a conduction problem. But this conduction problem doesn't have a steady state solution. And then it gets very tricky. So what they did is they tabulated in this super ugly way. Ying is way better than that, but it's taken years to get to that point. There are formulas to do this too properly, and good exponents and everything. They just didn't do that. They just give you these random numbers. My point here is that not only you can plug and chug whether you use this or this. I mean, you can kill this. This is easy. But what I want is when you look at this table, you say, aha, I know you. You're familiar to me. Okay, let's see more. Let's see more, because it's all like that, right? Spheres, right? And now spheres. We have, again, a formula. And see what we have here. Rayleigh to the 1/4, right? So Rayleigh to the 1/4 is laminar, right? It's what we know. What a big surprise, right? And something about the Prandtl, and this, they're fighting it whatever way they can, right? But if you look at the extremes of large and small Prandtl, this also speaks. I'm not going to worry much about this. Is this formula good for 0? For Rayleigh 0? Yes, it is, because we have these two that is saving us. Now, the sphere does have a steady state solution. These two here is exact. That 2 comes, remember when we looked at the dimensionless heat transfer, heat conduction coefficient, right? We looked at these shape factors and those things. Okay, if you do that convection, that conduction problem, right, and you express it in the form of a Nusselt number, you get exactly 2. This is awesome. Things come together. These 2 here it comes from conduction problem, and this 1/4 comes from laminar. And this Prandtl here, we can discuss that later. Let's not worry about that right now. The only thing that I don't know where it comes from is this weird 0.589, right? But see, it's never all to 0.85, 0.48. 0.589. You know what? If I have no idea what to say, you ask me what is my convection coefficient, I would say, yeah, probably 0.5 Rayleigh to the 1/4, right? And probably I wouldn't be that bad. Okay, now it gets another twist. Now internal flowing convection. Right? And now we have entry lengths. Everything you saw from internal flows now is the same, but we don't have an external velocity imposed. We don't have a UM to talk about. Right? So we have these formulas. This is for fully developed. This is for the entry length. Look at this. In the entry length, this exponential goes away. Right? After when we're deep into the entry length. Look what we have. You see this part here? It's the same as this. Right? It's the same formula. You see that? So here we have the Nusselt for the entry length. Here we have the Nusselt for the fully developed. And here you have for the case in which one side is adiabatic. So if one side is adiabatic, so the thermal boundary layer, if one side is adiabatic, right, is twice as big because it keeps developing until it reaches the other side. If the boundary layer is twice as thick, the Nusselt is going to be half as big. It all comes together, sure. Some of you might say, I'll plug and chug and forget everything. Fine, good. You'll be just as good an engineer as anybody else. But the pleasure? No. So this is a cool one. Enclosures. Now let's say the thing is inside a box, right? Thing is inside a box. And here's the box. The box has this, let's say the box is flat, so it has this thickness L, right? And the box can be at many different angles. Can be flat, can be standing, right? And we're going to define the heat flux as H times the difference in temperature between these two surfaces, right? T1, T2. Constant surface temperature. All right, if it is flat, all right, and again, trying to put things together. If it is flat, and I hit the top, right, do I have a natural convection? What do you think? No, because the hot goes to the top and it stays at the top, so case settled. So in that case, it's just conduction. Now, if it is a flat enclosure and I hit the bottom, now things are different because the hot wants to go up. And the way it does Have you heard about self-organized criticality? Like, it's crazy stuff, right? So what happens is you get these rolls of convection, right? Because the air wants to go up, but if whatever goes up has to go down, right? And because it's enclosed, right? So you have these they call it conveyor rolls, right? And they're like gears. You see, one rotates one way, and the other rotates the opposite way. And these organized by themselves, and the size of these rolls you can calculate. We're not going to worry about that. For us engineers, the good news is, guess what? You calculate your Rayleigh, and then you have a formula. Something times Rayleigh to a power. In this case, it's 1/3. Right? Good. Good. We can calculate very sophisticated things. This is the one you like. Double pane windows. Right? Double pane window. And guess what? Right? When I first taught this class, I was so excited. I said, I'm going to figure out double pane windows once and for all. And I did. But the answer is the least interesting of all, but makes sense. If Rayleigh is less than 10 to the 3, right? Rayleigh is based on this thickness here. If it is 10 to the 3, then nothing happens. If we have no convection, what is a problem? Conduction. It's a conduction problem, right? And so if you make this distance between the two panes small enough, Rayleigh becomes small, right? And we know that Rayleigh has this characteristic length to the cube, right? So actually very quickly I can kill Rayleigh. So this is a cool thing. The double pane windows, right, will give you an insulation as if they had just like wool, as if the air is not moving there, it's stationary. It's awesome insulation. Why would I have a triple pane window? Well, what would happen is if the triple pane, now I take the middle pane, this L value would be pretty big, right? And it increases with the cube, right? So now Rayleigh would start giving me convective flows. And if I have convective flows, it kills my heat transfer. Well, actually, it doesn't kill it. It enhances my heat transfer. It kills my insulation, right? Isn't that awesome? There's another thing. Remember when Ying showed that actually for the chimney case, radiation is more important than convection, right? In this case, because the air is so insulating, you forget about everything. Your problem starts to become radiation between the two panes. And that's why some of the high-end windows, they come with these special reflective coatings and everything, right? That is so thermal radiation. When we see radiation, you're going to see if something is very shiny, actually it exchanges very little heat by radiation, right? This is super interesting. Double pane windows, I got them now. I was hoping there was some crazy correlation, but no. It's just make sure there is no convection. Now, if the gap is big enough, then we are going to have all these convective flows, and we have formulas depending on H over L, right? H would be how high the window is, and L is how thick, right? And here you go. Guess what? The Rayleigh to the something, right? And the something is 0.29, that is so close to 0.3, right? And you could calculate it. But the fun thing of windows, no, you don't, right? It's just conduction. Cylinders. For concentric cylinders, they try to be smart and they use a different approach. In the end, should all be the same. What they say, this formula, I want to hear that you're familiar with this formula. This is a formula of conduction in a cylinder, right? Between the conduction between inside and outside. So you know this formula, except that this K for us was the K of whatever is inside here. And we used to talk about a solid, so it's only conduction. But here we have a formula based on Rayleigh to the 1/4 again, right? That says, okay, how should we account for a variation in enhancement of conduction because of the convective flows. So you have an effective coefficient here, right? So you say, okay, I'm going to assume it's convection. I'm going to assume it's conduction, but at an enhanced level, more than just if it was pure air. You follow this? Okay, there are problems which I mark. I cannot do all the problems here, which I would love to, but I marked the problems to do that are in the book, right? The book solves one of these problems. Spheres, same story. You have a KF that is somehow a Rayleigh to the 1,4. The story remains the same, right? And now, have 5 minutes, but imagine you have both convection, both natural convection and forced convection, right? The problem is tricky. It's impossible to do. So this is the engineering shortcut. So you calculate your free convection problem, then you calculate your forced convection problem, you calculate your natural convection problem, right? Now you calculate two problems, and then you combine them using this exponent, right? For example, in this case, let's say it's a cylinder, right? You would use n equals 4.